Good afternoon, everyone. So we'll be starting with the magnetism part second. We will be discussing some of the questions and charge in a magnetic field as well, right? So we'll be discussing some of the important questions as well as the previous year questions of magnetism part second, right? So let's begin with the first question here. The first question is a hollow cylindrical wire carries a current 5 amperes, having inner and outer radii R and 2 respectively. A magnetic field at a point which is 3r by 2 distance away from its axis is. The radius of the cylinder is R is given as 5 meters, right? So the question is that the question is like this. Uh, Let me just draw the cross section of this cylinder, right? Cross section of this cylinder. The cylinder is like this. It's a hollow cylinder, right? It's a hollow cylinder, right? Uh, Having the inner radius R and the outer radius capital R. This is the hollow cylinder here, right? This is the cross section of the cylinder. The cylinder is having the inner radius R and the outer radius 2R, right? And the outer radius 2R. Now we have to find the magnetic field at a distance at a point which is 3r by 2 at a distance of 3r by 2. It means that that point will actually lie between the two circular portions, right? It will lie between the two circular portions somewhere here, right? Somewhere here. Let's suppose this is the point P in between the two circles, right? This is the point P in between the two circles where this point P lies, right? And at this point P, we have to find the magnetic field, right? At this point, we have to find the magnetic field, right? Now, you can see that since this is a hollow portion, right? This is a hollow portion, right? If this is a hollow portion, and in this hollow portion, the magnetic field will be zero, right? In this hollow portion, magnetic field will be zero because according to Ampere's circuit law, integral of B dot dl will be equal to mu naught I enclosed, right? Mu naught I enclosed, and here the enclosed current is zero. Enclosed current is zero, so magnetic field inside this hollow cylinder will be equal to zero because of no current present inside this hollow part, right? So the current is actually only present in this part. Let me represent the current coming out of this cylinder with these dot points, right? Dot points, right? Let's suppose the current I is flowing through this circular portion, right? That lies between the inner circle and the outer circle, right? So let's suppose this is the current I, right? This is the current I. Now we know that we have to find the magnetic field at point P, right? At point P at a distance of 3r by 2. Once again, what we can do is that we can draw an Amperian loop at this point, right? We can draw the Amperian loop at this point. So we can draw the Amperian loop at this point. So this is the inner circle, right? This is the inner circle. And let's draw the Amperian loop, right? Let's draw the Amperian loop at this point. So this will be the Amperian loop. So this is the Amperian loop, right? With the red color, this is the Amperian loop here. And let's suppose at a distance of small r, the Amperian loop is the radius of this Amperian loop is small r, right? Now we'll be doing all the calculation on this Amperian loop, right? Now we know that according to Ampere's circuit law, integral of P dot dl will be nothing. It will be equal to mu naught times current enclosed, right? Current enclosed. Now the current enclosed we have to calculate because of through this Amperian loop, right? We know the current density through this hollow cylindrical wire is a constant, right? It's a constant, and the current density will be the current divided by the perpendicular area, right? And the current is actually flowing on this area only, right? In this area only, right? In this portion of the area, the current is flowing. So it means that we'll be just taking this area for calculating the current density for the cylinder, right? We'll be just taking this much of area for calculating the current density. Let's suppose current is I. So the current density will be I upon the perpendicular area, right? Now the perpendicular area will be because of this portion only, right? So that will be the area of larger circle minus area of the smaller circle, right? The area of the larger circle upon the area of larger circle minus the area of smaller circle. The area of larger circle will be 4 pi r square, right? minus area of smaller circle will be pi r square, right? That will be equal to I upon 3 pi r square, right? This is the current density. This is the current density, and it has to be a constant for this hollow cylindrical wire, right? So it means that the current density should be constant for this Amperian loop as well, right? It should be constant for this Amperian loop as well, right? So the current enclosed within this Amperian loop will be, it has to be equal to, the current enclosed within this Amperian loop will be equal to, that will be equal to I upon I enclosed, right? I enclosed upon the area, right? Upon the area. Now we know that for this Amperian loop here, for this Amperian loop, in this area, there will be no current enclosed, right? In this area, there will be no current enclosed. So the current will be only enclosed in this portion, that is pi r square minus pi r square minus pi capital R square, right? So this will be the value of current density, right? And it has to be a constant, right? So from here, pi and pi will get cancelled, right? Pi and pi will get cancelled. We'll get the value of enclosed current here. That will be I times R square minus capital R square upon 3R square. So this is the enclosed current here, right? This is the enclosed current here. Now let's substitute the value of the value of this small r and the capital R, right? The value of I is given here as 5, right? The value of the small r is given as 3r by 2. So it will be 9r square upon 4 minus r square, right? Divided by 3r square, right? 3r square. So it will be 5 into 5r square, right? 5 into 5r square upon 12 r square, right? Upon 12 r square. So from here, r square and r square will get cancelled. We'll be left with 25 over 12, right? So this much will be the current enclosed, right? This much will be the current enclosed, right? So the magnetic field at this point will be, it will be P will be a constant. It will be V times 2 pi r, right? 2 pi r. The value of r is 3r upon 2, right? 3r upon 2. That will be mu naught times I enclosed. That's 25 upon 12, right? 25 upon 12. So from here, the magnetic field will be nothing. It will be mu naught 25 upon 12, right? Divided by 6 pi r, right? Divided by 6 pi r. So this will be the magnetic field here in this region, right? So we can write it as 25 upon, it will be 72, right? 72 pi, right? Multiplied by r. The value of r here given is, that's equal to 5, right? 5 and 5 it will go. So it will be 5 upon 72 pi. So this much of magnetic field will be there in this region, right? This much of magnetic field will be there in this region, right? So this will be the magnetic field here because of this current, hollow cylinder carrying current 5 amperes, right? At a point, at a distance of 3r by 2 from its axis, right? Now let's move on to the next question. The next question is about a long straight wire carries a constant current distributed uniformly over a cross section, right? There is a long straight wire, right? And we know that the straight wire is assumed to be cylindrical in nature, right? It's assumed to be cylindrical in nature. Let's suppose this is the wire, right? This is the long straight wire, right? This is the long straight wire, right? This is the long straight wire, right? Of radius 3 mm, right? The radius of this wire is given as 3 mm. That is 3 into 10 to the power minus 3 meters. So this will be the radius of this wire. It carries a constant current which is uniformly distributed, right? Which is uniformly distributed. Let's suppose the current it carries is I, right? The current I is flowing through this wire, right? The current I is flowing through this wire perpendicular to the axis of the wire, right? Perpendicular to the axis of the wire. If the current density is 50 amperes per meter square, right? The J value of J is given as, that's the current density, that's 50 ampere per meter square. This much of current is flowing through the wire, right? The magnitude of the magnetic field at 1.5 mm, right, from the axis of the wire and 4 mm from the axis of the wire is, right? So we have to find the magnitude of the current, right? Now we know that inside a cylinder, inside a cylindrical wire, the value of the magnetic field is nothing. It's mu naught I into R divided by 2 pi R square, right? So this is the magnetic field inside, right? This is the magnetic field inside. And the magnetic field outside is nothing. It's mu naught I upon 2 pi R, right? This is the magnetic field outside, right? Now we know that I upon pi r square is nothing. I upon pi r square will be nothing. I upon pi r square here, it will be nothing. It will be the current density here, right? It has to be equal to current density, right? So I upon pi r square will be the value of that will be equal to J. That's nothing. That's current density, which is given as 50 amperes per meter square, right? Similarly, if you multiply here with r square and divided by r square as well, right? We can replace this pi r square with current density. I upon pi r square with the current density. It will be mu naught J multiplied by r square, right? Upon 2r, right? Upon 2r. So this will be the this will be the magnetic field outside in terms of the current density, right? In terms of the current density, right? Similarly, the magnetic field inside will be in terms of current density, it will be mu naught R upon R2 multiplied by J. So this is the current density magnetic field in terms of the current density, right? Now we have to find the magnetic field at a distance 1.5 mm from the axis of the wire, right? So we'll write here mu naught has the value 4 pi into 10 to the power minus 7, and the radius, the value of r here is given as 1.5 mm. So it will be 1.5 multiplied by 10 to the power minus 3 meters, right? And the value of current density is 50, right? It is 50 amperes per meter square, right? Divided by the 2, right? So 2 and 2 will get cancelled here, right? We'll be left with it will be 2 pi, right, multiplied by 1.5, right, multiplied by 5, right? So it will be minus 10 and 1, that will be 10 to the power minus 9, right? So it will be pi times 1.5 pi times 10 to the power minus 9, right? Minus 9, right? So that's the value of this much of magnetic field will be there. That's 1.5 pi into 10 to the power minus 9 Tesla, right? This much of magnetic field will be there, right? Or we can write it 1.5 pi nano Tesla, right? Nano Tesla. So this much of magnetic field will be at a distance of 1.5 mm, right? This much of magnetic field will be there at a distance of 1.5 mm from the axis of the wire, right? Now, similarly, if we have to find the magnetic field at a distance of 4 mm, right? At a distance of 4 mm. So this point will actually lie outside the cylinder, right? And we know the outside this cylinder, the magnetic field is given by this equation, that is P naught will be equal to mu naught, that's 4 pi into 10 to the power minus 7 multiplied by the current density 50, right? Multiplied by the current density 50. And we have the value of R here, value of R as the radius of this cylinder, right? That's 3 mm. That will be 3 into 10 to the power minus 3 whole square, right? Upon 2R, right? Upon 2R. The distance at which you have to calculate it is 4 mm. That will be 4 into 10 to the power minus 3. Now you can just calculate, you can just evaluate this values, right, for the magnetic field outside the cylinder, right? So this is how we can calculate the magnetic field for the cylinder inside the cylinder as well as outside the cylinder, right? This we discussed in the last lecture as well, right? Let's move on to the next question, right? Moving on to the next question here, right? The next question is that a closely wound solenoid, right? We know that the magnetic field due to solenoid, let's suppose this is the solenoid here, right? This is the solenoid, right? Let's suppose this is the solenoid, right? And length, if length of the solenoid is L, right? And then the number of, if N is the total number of turns, then the number of turns per unit length is N by L, right? And the magnetic field of the solenoid along its axis is given by, let's suppose this is the magnetic field lines because of this solenoid, right? These are the magnetic field lines, right? Because of the solenoid. And this magnetic field, because of the solenoid, is nothing that's equal to mu naught times Ni, right? Mu naught times Ni. Let's suppose the current I is flowing through this solenoid, right? Where N is nothing, it's the N is equal to number of turns per unit length. Number of turns per unit length. That's the value of N, right? Where I is the current flowing through it. So we have the similar question here. A closely wound solenoid 80 centimeter long has 5 layers of winding of 400 turns each. It has 5 layers of winding of 400 turns each. The diameter of the solenoid is uh, 1.8 centimeter, right? If the current carried is 8 amperes, right? Estimate the magnetic field inside the solenoid. So there are actually 5 layers of the winding, and each winding is having actually 400 turns, right? 400 turns, or we can see the total number of turns for 5 layers will be here equal to 2000, right? And the length of this solenoid is length of this solenoid is 80 centimeter, right? It's 80 centimeter. Now let's find the value of n, that's number of turns per unit length. That will be 400 upon 80 centimeter, that will be 0.8, right? That will be equal to 4000 upon 8, right? It will be 500, right? It will be 500. So the number of turns per unit length is actually 500, right? So there are 400 turns for 80 centimeters. So for 1 meter, there has to be 500 turns, right? So there has to be 500 turns, right? So the value of n comes out to be 500, right? Now, the diameter of the solenoid is given as 1.8 centimeter. If the current carried is 8 amperes, right? If the current carried is 8 amperes, estimate the magnetic field, right? The magnetic field, because of the solenoid, is nothing. It's mu naught Ni, right? It's mu naught Ni. The value of mu naught is 4 pi into 10 to the power minus 7. The number of turns per unit length is given as 500, and there are five such layers, right? There are five such layers. We will multiply it by 5, right? To get the total magnetic field, and the current flowing through the solenoid is 8 amperes. So this will be the total magnetic field, right? So it will be equal to it will be 4 pi multiplied by 8, right? It will be 2.5, right, into 10 to the power 3 into 10 to the power minus 7, right? So it has to be equal to 32, right? 32 pi multiplied by 2.5 into 10 to the power minus 4, right? Or we can write it equal to 3.2 pi into 2.5, right, into 10 to the power minus 3, right? So the value of pi is nothing, it's 3.14, right? It's 3.14. Or we can write it as 22 upon 7 as well, right? So it will be equal to 1.6 pi multiplied by 5 into 10 to the power minus 3, right? So it will be equal to it will be 30, right? 8 pi, right? It will be 8 pi, right? 8 pi into 10 to the power minus 3 Tesla. So this much of magnetic field will be along the axis of this solenoid because of these winding of 400 turns each, which has 5 layers of winding, right? So this will be the total magnetic field because of the solenoid, that's given by mu naught Ni, right? Now let's move on to this concept, another concept here, right? The concept is about from the path followed, identify the nature of charge on the particle, right? We have to identify the nature of charge on the particle, right? Nature of charge on the particle. Now you can see here, we know whenever a charge enters a magnetic field, right, with some velocity, it experiences some magnetic force, right? So that it's based on the charge in a magnetic field, right? It's based on charge in a magnetic field, right? Charge in a magnetic field. And if there is only a magnetic field present in a region, right, then the magnetic force acting on the charged particle will be nothing. It will be Q V cross B, right? So this will be the amount of the magnetic force acting on a charged particle, right? Where Q is the charge of the particle, V is the velocity of the particle, and B is the magnetic field vector in the region, right? Now you can see here there's a magnetic field into the plane of this paper, right? Into the plane of this paper, this is the direction of the magnetic field, right? I can see here for the charged particles second, right, there is no deflection, right? There is no deflection at all, right? This deflection is only possible, no deflection is only possible here in this case. There are two cases where the deflection is not possible or the force will be zero, right? If the force is zero, then if the force is zero, right? If the force is zero, right? If the force is zero, on the particle, right? There will be only two cases, right? The case one is either the particle has no charge, right? If the either the particle has no charge, right? Or we can say V cross B is equal to zero, right? V cross B is equal to zero, or we can say that the angle between velocity vector and the magnetic field vector is 0 degree, right? If velocity vector and magnetic field vector are along the same direction, then in that case the net force on the particle will be zero, right? So there are two cases only. One case is either the charge of the particle is zero, or velocity vector and magnetic field vector are parallel to each other, right? So here we can see here that the velocity vector is not parallel, but it is perpendicular to each other, right? For this particle second, right? The velocity vector is not parallel, but it's perpendicular to the magnetic field vector, right? It means that it means that this condition, this possibility is not possible, right? If this possibility is not possible, then the only possibility here is the charge must be equal to zero, right? The charge must be equal to zero. So it means that the second particle will be a neutral particle, right? It will be a neutral particle. So second particle has to be a neutral particle, right? So next second particle will be a neutral particle here, right? Now let's talk about the charge. Let's talk about the first particle, right? It means that the two particles are showing some deflection, so definitely they are charged particles, right? Now this particle is showing a deflection along this direction, right? It's showing a deflection along this direction. Then it means the force acting on this particle is along this direction. This will be the direction of the force acting on this particle, right? If this is the direction of the force acting on the particle, this will be the deflection for this particle, right? Now let's see how it is possible to have the net force along this direction. So it means that if magnetic field vector is into the plane of this paper, right? If the magnetic field is into the plane of this paper, right? If the magnetic field is into the plane of this paper, right? And the particle's velocity is along this direction, right? And the particle's velocity is along this direction, right? Right? Then the V cross B has to be in the upward direction, right? V cross B has to be in the upward direction. It means that if V cross B is in the upward direction, it means that this particle will be actually a positively charged particle, right? So particle 1 will be actually a positively charged particle, right? Positively charged particle, right? It will be a positively charged particle, right? And talking about the third particle, you can see the force on this particle, according to V cross B, the direction of the force should be along, the direction of the force should be along for the positive charge, it should be along this direction, right? But the force on this particle is along this direction because this is the nature of the path of this particle. It means that this is only possible if the charge on this particle is a negative charge. It means that the third particle is actually a negatively charged particle, right? It's actually negatively charged, right? Negatively charged particle. It's actually a negatively charged particle. So the particle third is actually a negatively charged particle, right? So the particle one is a positively charged particle, second particle is neutral particle, and the third particle is negatively charged particle, right? Now let's move on to the next question, right? A proton, neutron, and an alpha particle are going perpendicular to magnetic field. Then find the ratio of their radii if they are moving with same speed, with same momentum, with same kinetic energy, and through same accelerating potential, right? Let's discuss this one by one, right? Let's discuss this one by one. Now, we have to calculate the ratio of their radii, right? Now, let's suppose whenever the magnetic force acts on the particle, right? That's given by QV cross B, QV cross B, right? And if this is the only if this is the only force acting on the particle, let's suppose the particle is having a velocity along this direction, right? It's having a velocity along this direction, right? And this is the velocity, right? And the magnetic field is perpendicular to this particle, right? Magnetic field is perpendicular to this particle, right? Then the direction of the V cross B will be along, it will be perpendicular to the plane of V and B, right? And the particle will start move in a circular path, right? And this particle will have a circular path, right? Circular path. The trajectory of this charged particle will be circle, right? It will move in a circle, right? It will move in a circle, and the maximum force acting on this particle will be QVB, right? And that will be equal to the centripetal force, that's mv square upon r, right? Mv square upon r. So from here, the radius of this particle will be nothing. It will be mv upon qb, right? Mv upon qb. So, or we can write it as the momentum of this particle upon the q multiplied by b, right? So this will be the radius of the particle, right? Radius of the particle. So according to this equation, right, if they are moving with the same speed, if they are moving with the same speed, velocity is same, right? Magnetic field is same, right? Mass will be different, charge will be different. Then in that case, the R will be proportional to M upon Q, right? M upon Q. So we can use this equation. We can use for this condition. We can use this equation. R is proportional to M upon Q to calculate the ratio of radii, right? Similarly, with same momentum, if momentum is same, magnetic field is same, right? Then in that case, R will be proportional to inversely proportional to the charge of the particle only, right? And for the with the same kinetic energy, now let's suppose uh, R is equal to P upon QB, right? R is equal to P upon QB, right? In that case, we can write P equal to, relation between kinetic energy and the momentum is P square upon 2m. That's equal to kinetic energy, right, of a particle, right? Or we can say that the momentum of the particle will be nothing. It will be 2 times m into k, right? We can replace momentum here under root of 2m kinetic energy upon charge P, right? Now, for this case, the radius will be proportional to root of kinetic energy, right? Root of kinetic energy upon kinetic energy is same here, right? The kinetic energy is same, right? So it will be actually R will be proportional to root of m upon q, right? So this will be the ratio. This will be the condition for this case, for the third case, on which the ratio of the radius will depend, right? It will depend upon the root of m upon q. And the third condition is that through same accelerating potential, right? Through a same accelerating potential, right? The kinetic energy of the particle is given as charge multiplied by the accelerating potential, right? Charge multiplied by the accelerating potential. So now if we multiply here with the kinetic energy with replace the kinetic energy with charge multiplied with accelerating potential, right? That is V upon QB, right? V upon QB. So from here, so it will be under root of 2mqv upon QB, right? So from here it will be we can write it equal to root of 2mv, right? Upon root of q into b, right? So this will be the radius, right? So in this case, the radius will be proportional if they are moving with the same accelerating potential. Radius will be directly proportional to under root of m upon q, right? Under root of m upon q. So this will be the variation of the radius of a charged particle with different condition, with same speed, with same momentum, with same kinetic energy, and through same accelerating potential. So these are the different equations that we have written here, right, with respect to the radius of a particle in terms of different physical quantities, in terms of the momentum, in terms of the mass velocity, in terms of the kinetic energy, in terms of the accelerating potential, right? So these are the equations, right? These are the equations that we can write for this charged particle, which is moving in a circular path because of the magnetic field, right? Now, let's discuss this important question, right? Let's discuss this important question here, right? There is a charged particle enters in a transverse magnetic field as shown in figure, then find the deviation angle, right? Deviation angle, right? Deviation angle. Let's suppose this charged particle enters at an angle of theta here, right? This charged particle enters at an angle of theta, right? And once this charged particle enters the magnetic field, the path it will experience magnetic force, and because of that magnetic force, the particle will try to move in a circular path, and the path will be like this, right? The path will be like this, right? And at this point, the particle will actually escape the magnetic field once again, right? The particle will not complete the circle, right? Will not complete the circle at this point. It will escape the magnetic field from this point, right? And once again, it will make an angle of 45 degree here, right? It will make an angle of 45 degree, or we can say it will make an angle of theta, right? It will make an angle of theta here. It means that the total angle covered by this particle, the total angle covered by this particle during the in this magnetic field will be actually twice theta, right? It has to be twice theta, right? Because I can see here the deviation here is actually, if we shift this velocity vector here, right? If we shift this velocity vector here, right? If this is theta, this has to be theta. It means 2 theta will be the total deviation, right? Total deviation. 2 theta will be the total deviation, right? 2 theta will be the total deviation. It means that for this question, the total deviation will be 2 times 45 degree, right? It will be equal to 90 degree, right? 2 theta will be the total deviation here, right? The total net deviation for this particle will be 45 degree, right? It will be 45 degree, right? And similarly, you can see here, if we draw a perpendicular to this point here, if we draw the perpendicular to this point here, right? This is the perpendicular to this point, and this is the perpendicular to this point. And this distance will be actually this perpendicular distance will be actually the radius of its circular path. This will be the radius of the circular path. And this angle here will once again be equal to 90 degree, right? This angle here will be once again equal to 90 degree, right? So the total deviation will be here 2 theta, that's 90 degree, right? Now the question is time for which the particle remains in magnetic field. Time for which particle remains in the magnetic field, right? We know that when a particle moves in a circular path, right? Particle moves in a circular path, right? It completes an angle of 2 pi in one complete time period, right? It means that once the particle is in a magnetic field, so the angle covered by the particle in one time period is the 360-degree angle, right? It's the 360-degree angle. But now the particle does not remain in an angle, does not cover the angle of 2 pi here. In this case, it covers only the angle of 2 theta here, right? 2 theta. It means that the angle, the time spent by this particle in this uh, in this magnetic field will be nothing. It will be t times multiplied by the angle 2 theta upon the 2 pi, right? Upon the 2 pi, right? That means that this will be the time period, right? This will be the time spent by the particle in the magnetic field. That will be 2 times 2 theta upon 2 pi, right? Or from 2 and 2 will get cancelled. We're left with uh, t multiplied by theta upon pi, right? It means that this will be the time spent by the particle in a magnetic field, right? Time spent by the particle in a magnetic field, right? In a magnetic field. So this will be the time spent by the particle in a magnetic field, right? And talking about the time period, right? When the particle moves in a circular path, right? The radius of this circle is r, right? And we know the radius of the circle is given by mv upon qb, right? It's mv upon qb, right? Now the time period of the circular path will be nothing. Time period of the circular path will be equal to, it will be the circumference of the circle upon the velocity, right? That will be 2 pi r upon v, right? Now we can replace this 2 pi, we can replace this r with mv upon qb. It will be mv upon qb, right? mv upon qb right here. And there will be factor v, right? V and will get cancelled. So the time period of this particle is nothing. That's 2 pi m upon qb, right? 2 pi m upon qb. This is the time period in a circular path, right? This is the time period in a circular path. It means the time spent by the particle will be nothing. Pi and pi will get cancelled. It will be twice m into theta, right? Twice m into theta, right? Twice m into theta upon qb, right? Upon qb. So this will be the total time spent by the particle in a magnetic field, right? This will be the total time spent by the particle in a magnetic field. And if it enters at an angle of theta in the magnetic field, right? So 2 m theta upon qb will be the time spent by this particle in a magnetic field, right? Displacement of a particle when particle emerges out, right? Now you can see here the displacement of this particle will be from this position to this position, right? This is the total displacement, right? This is the total displacement, right? This is the total displacement here. If this is the total displacement here, now you can see here in this case, you can see it is the total displacement, right? Now, if this is the, let's suppose if this is the theta, then this angle has to be theta here, right? This will be theta here, and this has to be a theta here, right? This will be theta, right? Now we can resolve this r into two components. This will be r cos theta, right? And this component for this r will also be r cos theta here, right? So the total displacement will be actually it will be r sin theta, not r cos theta. So the total displacement here will be equal to twice r sin theta, right? Twice r sin theta. So this will be the total displacement, right? We need to remember this equation. The total displacement here will be 2r sin theta, and the time spent in the magnetic field will be 2mq upon qb, right? Now you know the value of r. We can put the value of r. The value of theta here is 45 degree, right? We can substitute the value of 45, that will be 2r upon root 2. This will be the total displacement, right? In general, the displacement in the magnetic field will be nothing. It will be 2r sin theta, and the time spent in the magnetic field by the particle will be 2m theta upon qb, right? This will be the time spent by the particle in a magnetic field, right? This will be the total time spent by the particle in a magnetic field, right? Now let's move on to the question number 7, right? The question number 7 is that a particle of mass m charge q is projected into a region having a perpendicular uniform magnetic field P of width D. Find the angle of deviation Q of the particle as it comes out of the magnetic field, right? So the question is like this. The question is like this. Let's suppose This is the magnetic field, right? This is the region of magnetic field here, right? This is the region where the magnetic field is present, right? Now a charged particle, right? If the charged particle is projected, right, into a region, let's suppose the charged particle is projected into this region, right, like this. If this is how the charged particle is projected into this region, right? Then in that case, in this case, the particle will follow this trajectory because of the magnetic force acting on it, right? And it will leave the trajectory. It will leave the magnetic field at this point, right? It will leave the magnetic field at this point. The width of this magnetic field is given as the width is given as t, right? This is the width of this magnetic field region, right? I can see here. You can see here. If this is the trajectory of this particle, we'll draw the perpendicular at this point. If this is the perpendicular at this point, it means that this will be actually the radius of this particle, right? And it will leave at an angle of theta here, right? We have to find the angle of deviation, right? We have to find the angle of deviation, right? It will leave the region here at an angle of theta here, right? It will leave the region at an angle of theta here, right? So this will be the angle of deviation here, right? If this is the angle of deviation here, right? We have to find, we know that the deviation in a magnetic field is nothing. Deviation in a magnetic field is always uh, deviation in a magnetic field is nothing. It's always equal to twice of theta, right? We know the total deviation here is twice of theta, right? It's the twice of theta, right? And now you can see here, it is the twice of theta. Now, angle it was making with this magnetic field region here is this is the angle it was making, right? Now, let's suppose this particle is entering the magnetic field along this direction. It's entering the magnetic field along this direction, right? It means that the angle which it makes initially with the magnetic field is the 90-degree angle, right? It's the 90-degree angle, right? It's the 90-degree angle, right? So this is the angle at which the particle is entering the magnetic field, right? It's entering the magnetic field, right? And we know the net deviation for the magnetic field for the particle to leave the magnetic field is actually twice of theta, right? It's actually twice of theta, right? That means that at some angle, this particle must be leaving this magnetic field, right? If theta 90-degree is the angle at which the particle is actually entering this magnetic field, right? So it must be, it means that the particle must leave the magnetic field once again at an angle of 90-degree, right? This particle must leave magnetic field at an angle of 90-degree. We can redraw this path of this particle, right? So it's entering at an angle of 90 degrees. So this particle must leave the magnetic field at an angle of 90 degree like this, right? So this will be the path of this particle, right? So this will be the path of this particle. So it enters at a 90 degree and leaves at the 90 degree, right? So the net deviation here is net deviation will be here equal to twice of theta, right? That will be equal to 2 into 90. That will be equal to 180-degree, right? This will be the net deviation, right? If it enters at an angle of 90-degree, right? So net deviation here in this case will be 180-degree, right? Now let's move on to the another question, right? A proton accelerated by a potential difference of 500 kilovolt moves through a transverse magnetic field of 0.51 Tesla shown in the figure, right? The angle theta through which the proton deviates from its initial direction of its motion is, right? And we know that once again the deviation is nothing, it's twice theta, right? Deviation is the twice theta. A proton accelerated by a potential difference of 500 kilovolt moves through a transverse magnetic field of 0.5 Tesla, right? As shown in the figure. The figure in this question is missing, right? The figure in this question is missing, but the deviation has to be equal to twice of theta, right? Twice of theta, right? So this will be the net deviation for any particle entering the magnetic field, right? So since the figure of this question is missing here, right? We'll be discussing the same question later on, right? So let's move on to the question number 9 here, right? Question number 9 says that a charge of mass q of charge q and mass m, right? Charged particle of mass m and charge q projected with velocity 3I cap plus 4j cap in external magnetic field, right? The magnetic field is giving along the direction of I cap. That's 60 I cap, right? We have to find the radius of circular path, pitch, and time period, right? We have to find the radius of the circular path, pitch, as well as time period, right? I can see here. Let's suppose if we project a particle at an angle of with velocity v at an angle of theta with respect to the magnetic field, right? So there will be two components of this velocity vector, right? One component will be along the vertical direction, that is v sine component, that will be v sine of theta, right? And this component will be v cos theta, right? Now, because of this v cos theta component, there will be no magnetic force because of this v cos theta. It will be only because of the v sine theta, because when the velocity is parallel to the magnetic field, there is no magnetic force. So the only velocity component will be which will be responsible for the magnetic force will be the vertical component, that's v sine theta, right? And because of this v sine theta, v sine theta, there will be magnetic force acting on this particle, and because of this v sine theta, the particle will try to move in a circular path, right? The particle will try to move in a circular path. But apart from the particle component, there is one more component. There is one more component for this particle, that's the horizontal component. And because of this horizontal component, the particle will try to move in a horizontal direction. So because of vertical component, the particle tries to move in a circular path because of the magnetic force. But the horizontal component of the velocity of this particle will drift the particle along the horizontal direction, right? So the path of this particle will be like this. It will be helix, right? So the path of this particle will be helical in nature, right? It will be helix, right? So helix will be the path of this particle, right? Helix, right? Now talking about the time period, right? A time period, right? Now the time period or the radius of the circular path will be nothing. Radius will be once again, right? It will be mv square upon r, right? Now there is which component? This is the perpendicular component which is responsible, right? It will be v perpendicular square upon r, right? That will be equal to uh, qbv sin theta, right? Qbv sin theta, qbv sin of theta, right? So it means that the radius will be nothing. Radius will be here equal to mv perpendicular upon qb, right? So this will be the radius of this particle, right? Radius of this particle, right? Now, the component which is perpendicular to the magnetic field here is J component, right? Because the velocity of this particle is given here, that's 3 I cap plus 4j cap, right? So it means the component of the velocity which is perpendicular to the magnetic field is the y component, right? This component. So the radius of this circular path will be decided by this component of the velocity. It means the radius will be m times p perpendicular, that's 4 upon qb. The charge is q, the magnetic field is 6 Tesla, right? So it will be 2m upon 3q, right? So this will be the net radius of the circular path, right? Now pitch we define it as it's the drift. In this drift we define it as the horizontal distance or drift for this charged particle along the horizontal direction in one complete time period, right? In one complete time period, right? The time period of this particle is nothing. The time period we calculated as it was 2 pi m upon qb, right? 2 pi m upon qb. This was the time period. And this time period is independent of the velocity, right? Velocity components, right? This will be the time period. Now this pitch is nothing. Pitch p is nothing. It's the distance traveled in one complete time period. That will be time period multiplied with the velocity along the horizontal direction. That will be v cos of theta, right? That will be v cos of theta, or we can say horizontal component, right? Now the horizontal component of this velocity is actually given as 3 I gap, right? So the drift of this pitch of this particle will be nothing. It will be 3 times a time period, that is 2 pi m upon q into b, right? The value of b here is given as 6 Tesla, 6 and 6 will go, right? So pi m upon q will be the pitch of this particle, right? So pitch of this helix is actually pi m by q, right? So this will be the pitch of this helix, right? Now let's discuss the question. Try to find the trajectory. Now you can see here the velocity vector is along the direction of the magnetic field, right? There is magnetic field and electric field as well, right? So let's see the magnetic force Fm will be here. That will be equal to qv cross b. Since the velocity vector is parallel to the magnetic field vector, right? So the angle between them will be actually 0, right? Sin theta here will be 0, or we can say v cross b here will be equal to 0, right? V cross B here will be 0. So it means that on this particle there will be no magnetic force, right? There will be no magnetic force, right? But the only force on this particle will be electrostatic force because of the presence of this electric field vector, right? And this electric force, if we assume this is a positively charged particle, let's suppose this is positively charged particle, right? A positively charged particle, then the direction of the magnetic force will be along the direction of the electric field for this positively charged particle, which is parallel to the velocity vector, right? That will be equal to QE, right? That will be equal to QE. Now you can see here the velocity, the net external force on this particle is only QE, and that force is also directed along the same direction as that of velocity of this particle. It means that the path of this particle will not change. The path of this particle will remain as straight line, right? It will remain a straight line, right? It will remain a straight line, right? So even if the positive, even if the sense of this, or we can see the charge of this particle is a negative charge, right? Then on that, in that case, the force will be opposite to the direction of the velocity, but still the trajectory of this particle will be a straight line in that case also, right? So the trajectory will change only if the electric field here would have been at an angle of theta, right? Then the trajectory of this particle would be parabola, right? So there are two paths only possible, only two paths possible, right? Uh, Here in this case, right? If the velocity, if the charge is positively charged, then still the path of this particle will be a straight line path. If the charge is negative charge, then in that case also the path of this particle will be a straight line path, right? And the effect on the speed, if the charge is a positively charged, then the speed of this particle will increase, right? For positive charge, we can say for positive charge and negative charge, trajectory will be a straight line, right? Trajectory will be a straight line, right? But for positive charge, since force is along the direction of the velocity, but for positive charge, speed increases, right? And for negative charge, since force will be opposite to the direction of the velocity, for negative charge, speed first decreases, and then increases in the opposite direction, right? So the for negative charge, the first for the negative charge, if this is a negatively charged particle, right, the velocity is along this direction, the electrostatic force will be along this direction, right? The force will first decrease, the velocity will first decrease, right? Means the particle will move forward, right? It will come at rest and will come back, right? And it means that the particle will actually reverse its direction at some point, right? And will once again move along a straight line path, right? With increasing speed, right? So this is it for this question, right? This is the trajectory of the particle and the speeds of the two charged particles, right? Let's move on to this question number 11. The question number 11 says that a particle having charge plus 5 coulomb moves with velocity 3 j cap in an electromagnetic field, right? If magnetic field is given as 3 I cap plus 2 j cap and electric field is given as 2 k cap, then find net electromagnetic force. The net electromagnetic force on this particle, right? That's the Lorentz force, right? So the net force will be, it can be a magnetic force, that's QV cross P, plus the total electrostatic force, that PQ multiplied by E vector, right? So this is the net magnetic force, right? This is the net force, electromagnetic force on this particle, right? Now, the value of Q here is given as 5 coulomb. The velocity vector is given here as 3 j cap, right? It is crossed with 3 I cap plus 2 j cap, right? Plus Q times 2 k cap, right? The value of Q is 5, right? K cap, right? Now the cross product between these two vectors will be, now J cross I, right? J cross I will be minus K, right? J cross I will be minus K, right? it will be minus 9 k cap, right? Minus 9 k cap, and j cross j will be 0, right? So that will be plus 10 k cap, right? So 5 nines will be, it will be minus 45 k cap, right? Plus 10 k cap, right? So the net force on this particle will be minus 35 k cap, right? This is the net force on this particle. It is along the k cap direction, right? So this is how we actually find the net electromagnetic force on a particle, right? In an electric field as well as magnetic field, right? This is a Lorentz force, right? So that's it for today, right? We'll be discussing this last question here, right? The last question is that find the force on a given wire in uniform magnetic field, right? Uh, the force on a the force on a current carrying wire in a magnetic field is nothing. That's given by integral of I dl cross B, right? I dl cross B, right? This is the force on a current carrying wire in a magnetic field, right? Now you can see here it's a semicircular wire, right? The effective length of this wire is nothing. This is the direction of the effective length, right? It's the direction of the effective length, right? L effective vector, right? And they are perpendicular to each other, right? So it means that the net force here in this case, I is a constant here. It will be integral of dl cross B, right? dl cross B. Now direction of dl vector and B vector is actually 90 degrees, so it will be uh, I B integral of dl, right? Integral of dl. Now integral of dl will give us the effective length of this magnetic field vector, right? Effective length of this magnetic field vector, right? That's equal to the value of I will be here. That's I, right? Magnetic field, it will be L effective, that will be 2R, right? 2R, and the angle between them will be 90 degrees. So it will be B multiplied by 2R, right? The net force on this particle will be nothing. It will be 2BIR, right? 2BIR. So this is the net effective force on a current carrying circular loop, right? Because of this magnetic field. So for any current carrying system, right? Current carrying system, the net magnetic field is IDL cross integral of IDL cross B, right? So this is how we find the magnetic force on our current carrying wire, right? So that's it for today. We'll be discussing further questions on this topic in the next part, right? In the next part of this chapter. Till then, take care and goodbye.